In the first half will be, I'll be discussing the concept behind catastrophe modeling and introducing a little bit some of the modeling methods we use and techniques that are popular in the field. The second half then is going to be a little bit more about my journey trying to apply what I've learned from Eugene. So I've been to this introductory course a year ago pretty much, and more recently I've been to the advanced course in machine learning, so I feel like I'm equipped to start using some of those tools. And I'll try and explain what I've learned so far and first models using those techniques. The outline, well, so I'm saying I'll start by describing what catastrophe modeling is. And we've had actually a really good talk 2 months ago, I think, here in the Data Science Sydney, from Alexander Pree, who was describing cat modeling from the point of view of the users, really, so the insurers and the brokers. I'll try and give a bit of a different view from the model developers. And he mentioned a few times that cat models for them look really like black boxes. So my point will be, okay, let's try and see what's inside the black box, at least a little bit. And I'll use models for tropical cyclones for that purpose. As I was saying then, I'll describe a little bit my diary so far, what I've done trying to apply these methods and just look at potential, really the good potential I've found and the challenges I can see. And we'll see a first little model that I'm actually quite proud of. The company I work for, so Risk Frontiers, is an independent R&D company that's 22 years old now. And our core business is really, we're trying to develop probabilistic catastrophe models, so the so-called CAT models. And the jargon of the industry, we're called model vendors. And you have quite not many companies that do that in the world. I think I can count 8 companies that would sell a model of that sort. And we are pretty small one, but we're the leaders in that side of the world, and we're slowly trying to expand building models for Asia. So what you have on the right here is the suite of models we're offering. You can see we're not very creative with the names, but it's quite easy to get what they are. So we study the risk of flood, hail, bushfire, cyclone in Australia, and earthquakes in both New Zealand and Australia. So this is our offering. The next thing I'll move on is what is actually a CAT model. And first, I think I have to say that it's a terrible name, because I was very confused at first when I started in that field, because it's not a model at all. What we're really selling is a huge catalog of events. So it's not just about randomly simulating disaster events, but essentially what it is a big catalog of events. And we're trying to have events that characterize the risk in a given region. So later on, I'll be talking about typhoon in Asia, and that would be, for instance, the risk you're trying to characterize. These are by nature, they're really rare events, so we have few observations. We can't rely on history to give us a picture of the risk. And that's the main challenge here. So what we do is try to use statistics and physics where we can to extrapolate history. Essentially, we're trying to produce alternative version of history to get a bigger pictures of what could happen, even though it's not happened yet. There is a misconception I'd like to clarify quickly, is we're not predicting anything. So our models will not be saying there might be 5 hurricanes next year and 1 in Florida, or anything like this. That's good because I think it's pretty much impossible to do, and it would be very risky to do because you get caught wrong. What we do instead is really assess the distribution of risk, or the loss distribution. And the product our clients will use will technically be used to generate things like the average annual loss an insurer might have on their portfolio, or things like what's the loss I can expect from a 1 in a 100-year event. And really the common metric in this field is this sort of curve, where you're looking at different loss thresholds, and you're looking at the probability of exceeding on any given year a certain loss threshold. Here, you look at, okay, if I'm looking at exceeding $100 million, well, I have a 1% chance of it happening on any given year. That is really the product we're after and we're selling to our clients. How we get there? Well, that's a part that the talk 2 months ago was really good on, and I think I'll be quite brief. But the idea is that we have a whole series of building blocks. The first one is what you have on the top left. It's what we call exposure. That's really about identifying what's the stuff at risk. So usually the building. Where are the buildings insured? What type of building are they? How old? What sort of protection they might have for hurricanes and things like this. So we're really building a picture of the exposure at risk. We then have a second part just below, which is the hazard component, and that's what I want to talk more about. And that is about generating a lot of events, and for each of those events, having a map of the risk. So this could be, if you're looking at floods, it could be a map of flood depth. It could be the ground shaking if you're looking at earthquakes, or in case of tropical cyclone, it would be maps of wind speed. We're then combining those two, and that's the block in the middle called vulnerability. The aim here is to say, okay, given a mean intensity, so again, it could be the ground shaking or the wind speed, what sort of damage will I be looking at? And typically we model first the mean damage we can have, but we also try to model the distribution around it. That's probably another place where machine learning could be very useful, but not for today. I'll try and look at this at another point. The final step then, once we have at that stage we have an image of the damage and damage ratio, the final step is the financial modeling. So we'll start to look at how much was the building insured for, what sort of premium, what sort of reinsurers maybe the clients have used, and we'll generate this sort of curve, which is essentially what our model was built for. But today, as I was saying, I'll focus really on that little part here, the hazard generation. And let's keep on narrowing down. So I've even been talking about different perils, but now we'll be talking only about tropical cyclones. What you have here is a map of all the tropical cyclone tracks, and the color refers to the cyclone categories. And you see first that it is a global, almost global problem. We have 7 different basins in which tropical cyclone occur. And to date, no one is really trying to model this as a global problem. So the way we do models in that sense is by basin. So I'll be focusing on the western North Pacific basin. Reason for this, well, is, as I was saying, we're trying to get into that space. But also, if you look at this, it's clearly the one where the most intense cyclones occur. And also, that's also where the highest rate of occurrence is. To characterize the risk in that basin, we're targeting 100,000 years of tropical cyclone activity. So that's what we want our catalog to represent. And if you think that you have on average 26 cyclones in that area per year, that means we're actually trying to represent 2.5 million or more cyclones. That is the aim of this model we're building. It's not, as I was saying, it's not just about generating 2 million cyclones. They also need to have a certain consistency with history. And that's an interesting topic always, because, and I guess if you ask a model user or model developer, we have different views on this. You have, obviously, history is the only thing we know for sure, but it's only 50 years really. So yes, we have to have some consistency with what has happened, but we want the model to do a lot more. So the trade-off is quite tricky sometimes. But the example I would take is if you look at Japan and the category 5, we know you have a lot of category 5 happening in Okinawa, for instance, but we've never seen one in Tokyo. Now we might want in our model because physics says, why not? We could have several Cat 5s in Tokyo, but we certainly don't want to have more Cat 5 in Tokyo than we have in Okinawa on a yearly basis. So we need to maintain this consistency that we know from history, but we want to go further than history, and that's the whole game. So I'll try and explain how we do this. And okay, the starting point is historical data, because that's all we know, really. And when we talk about historical data, we usually consider that we can rely on things after the 50s, really. So in that case, I've taken every track from the Japan Meteorological Agency, from 1950 and onwards. This is what you have on the plot on the right, every single track that occurred, and the colors are referring to the month at which they occurred. On the top left here, it's the location at which cyclones get started, what we call the genesis. So lower latitude is all the occurrence rates of those cyclones. And below that, you have a picture of the cyclone maximum intensity. So we measure that in terms of the minimum pressure, which is why the most intense cyclones are the one with the minimum pressure, which is the blue colors. So the latitude around the Philippines is really where you have the most drastic cyclones. And yes, if you just use this already, this is the view of risk you have. But we want to go further now try and talk about this black box. So how do we try and generate these 2.5 million cyclones? Well, we really go step by step, as you would imagine coding yourself, and we just decide, okay, we'll loop around that many years we've decided. So we want 100,000 years, as we're mentioning. So we'll go and loop through the years. On any given year, we'll first sample how many cyclones happening on that year. And this is usually done through Poisson. This is something that could be questioned, and I'll come to that a bit later, but the idea is we will present that as a Poisson process, and we sample how many cyclones occur on that given year. We then look through all the cyclones in that year, and start to decide what the track it has. So we'll find, according to history and where the cyclones have started, and sample genesis location, the start of the cyclone. And then we'll iteratively propagate the cyclone every 6 hours. So this is, well, usually every 6 hours. So you would go and compute your track, and along the track you will also compute the pressure, so the intensity of the cyclone as it evolves. Until you reach a point where, well, either the cyclone has become too weak, or it's gone over a mountain or something that triggers the death of the cyclone, so what we call lysis. And that is the first step where you decided where your cyclone is going and you decided how intense it is. We then come back, and there's a whole bunch of other parameters we need to estimate our wind risk here, such as the maximum velocity around the cyclone, which I'll call VM, the size of the cyclone, which we'll measure through the radius between the eye and the maximum velocity. I'll show that. And then you have different other parameters that come in depending on the model you're using. Once you have all those parameters, you can then project especially the wind risk. So that's the final step where you're like, okay, I've simulated my track, I've simulated my intensity, I've turned that into a wind characteristic, and this is how the wind distribution will be around my cyclone at each step. And I will now go a little bit more in the details of these three sections, just to give a flavor of how we do those things. So the track modeling, so coming back to what I was just saying, the first thing is where do we start the track? So for this, we base it on history, and we look at every location where we've had a cyclone in history, the rate at which that happened, and we then smooth it out to get a spatial density distribution. And then we'll randomly sample from that to get this sample genesis location. The third thing you need to do then is define all the parameters you're going to be at the first step. So we sample storm speeds, the heading direction, and the pressure from distribution that will likely depend on where you've started your cyclone. And then from there, because we have the starting heading and the starting direction, we can compute where the cyclone is going. So that's your first point 6 hours after the start. And then we need to update the parameters. So from that point on, what we try to model is the 6-hourly change in every one of these parameters. And this is done usually through autoregressive models. So the change in my heading direction in the 6 hours between the 2 points will be dependent on latitude, longitude, the heading itself before, at the time step before, and some random noise. We'll do the same for the speed. So that's how we update the speed of the cyclone along its lifetime. And similar for the pressure or the intensity of the cyclone. I'll note though that for the intensity, the models are a bit more complex because we know more from the physics, and we use physics, so things like the sea surface temperature average over a certain region, to constrain the range of parameters the intensity can take. And we then propagate that from 6 hours to the next point until you reach the whole life of the cyclone, and again, inside that the cyclone has finished. Just the reason I was talking about all these details is not necessarily to go into detail, but is to get a flavor of how we achieve the sort of variability we're after. And it's all about sampling and noise. So at every step, we need to model things through distribution, and we go through random sampling. And that's how we cover something that might be representative of 100,000 years of risk. It's just repeated random sampling. That's the key. I will not go through the models of wind parameters I discussed, but I just want to introduce them because I'll be using this a little bit more. So this is a picture of a cyclone heading straight north, and you have different ways to characterize the wind field. First, the radius of maximum wind. So that's the distance between the eye of the cyclone, the blue center here, and the darkest red, so the point of maximum wind. And that's the gray line you have going to the right. We then measure the angle where this occurs, and this is done relative to the heading. So you see this blue arrow is what we'll refer to the angle of maximum wind. We also need to know about the maximum velocity, what I call Vm, and that is very constrained by the physics, so we know how to model that quite well. And then depending on the model you use, you'll have other shape parameter things that will explain how the wind field decays after the peak maximums, and other depending on models. And then you have the model itself, so the actual wind field distribution. And there's a wide range of models that have been used, but they're all really based on the same assumption. And that's actually quite old by now. It's like models from the 80s. And it's really saying, okay, to model the cyclone, we can assume that it's an axisymmetric vortex, so this sort of big donut I've put on the left, which is what would happen if the cyclone is not moving at all. And then you add the velocity of the storm. So the second step, which I've put with this big arrow, is if we now say the storm will be moving to the left of the slide, we're adding vectorially the velocity, and we obtain what is our representation of the cyclone. So everything to the right will have gone faster, and everything to the left will have gone weaker. So that's assuming we're in the northern hemisphere. And that is the key assumption. Like, you will have much stronger winds on the right of the cyclone in the northern hemisphere than you have on the left. So to sort of wrap up this first part, to achieve viability in our CAT modeling, we have sort of three big weapons, let's say. Well, first, we need to simulate millions of tracks, so we use very simple models, very simple formulations. To achieve the sort of wide range of viability, we're after the key thing is random sampling, repeated random sampling of a wide range of parameters. And to sort of keep a safety net and constrain our parameters, we have sort of a lot of conception about the physics of what happens. You would, for instance, people assume that a cyclone moving to higher latitude will become bigger, and they will put that in the model because they think, well, it's what I believe physics does, and it's a good storytelling. So there's a whole process in there where people like to have a feeling for how the model behaves. And that's where the scope for machine learning is actually probably very interesting, so that you can start removing all these things. We don't actually need to come in and decide that, yes, I'm expecting storms to increase when they move north because I understand physics and I want this to happen. So that's sort of the big advantage I see, and that's what we'll be showing in a second. There are, however, a few challenges. First, really, we're studying rare events, so this is not big data. It's clearly a case where we're going to struggle with data. The second one is probably the challenge I see as the toughest, is the whole thing we're trying to do is train model on some data, but use it to extrapolate way beyond the data. So I don't know to which extent the algorithm we're using can cope with that. And the last thing is something that might become clear after, but we need to model not just the mean response. We really want to have the distribution every time. Everything we model along the way will after the distribution, and I'll talk about this a little bit more in a second. So the part of the model I've decided to attack first is the wind field model. So the wind field, the sort of donut approach I was discussing before. This is what you have on the left, and this really assumes that if the storm is moving to the left, you have everything to the right. Now what I've put here is a picture of the wind field from Hurricane Sandy. And it is at that state moving to the left. And you see that the framework is totally broken. That most of the wind is happening the other side of the track. And you could never simulate that with that sort of wind field formulation I was discussing. No matter how often you sample or whatever you do, the physics we've put in there, thinking was the right thing to do, is actually what prevents the model from doing things that we've observed. So that is, to me, a clear case where we've put too much trust into the storytelling, and we've decided that, yes, we like model to be built in that way, but actually, this is not the case. We've observed a lot of cases like this, especially in Japan. And so I think it's a good example of where we can relax that with machine learning. So that's the advantage I see. Don't have to put preconceived formulation in there. The challenge is the lack of data is even bigger than in other field, because in other part of the model, because it's really hard to get an image of the cyclone wind field. Satellite really struggle as soon as you have rain with it and so on. So this really is the challenge here. But the approach I've taken is to sort of create some data. So it's a bit strange because it's using another model. But the idea is to use a very complex, high-resolution model, the type you use to make weather predictions. It's a model, and it's also modeling the physics, but it's modeling so much more than the simple things we had, that at that stage it's probably the best thing we can do. So I'll show a little bit what I'm talking about. This is one of those simulations I've done. And you have a typhoon here, moving just above Taiwan. And that's one of those cases that pretty much goes as the the classical framework would do. That's, most of the wind is to the right of the storm. You see also, that's quite interesting, that as soon as one dies, another one forms, which is something we observe quite a lot in that part of the world. There's sort of clustering. That's not good with the Poisson assumption, but that's an interesting topic. And I'll show another one here, just another simulation, now moving to the south of Japan. And you see that this one is more of the kind that doesn't really follow the framework of everything to the right. You have strong winds to the left happening on the storm here, and they're actually quite often stronger on the left than they're on the right. So what I've done is to go through 30 of those cases. So yeah, that made it still not big data, but that's where I stopped to sort of start playing with these ideas and introduce concepts. So I've got 30 different storms. They're all simulated at hourly time steps. So that makes some 1,580 different sort of snapshots of wind field. And these are two examples. So the one at the bottom here is one good example of a case where all of the strong winds are to the left of the storm. So again, you could not represent that with the classic formulation. The next step I took is to sort of project all those 1,580 snapshots in a grid where I could compare them. So the standard grid I'm using is what I'm showing here, which is saying I'll have a grid of, it's 150 by 150. And for every wind field, I will put the eye of the cyclone at the middle of the grid, and I will have the maximum at the point 0.25. It's just a convention. That means all my cyclone will be on a grid that is dependent on the radius of maximum wind, but that allows build a model on there. I've also normalized all of them by their maximum wind. That means I'm trying to build a model that is just the shape. We forget about the intensity, we forget about the size, because this will come as input. And what I'm really trying to get is, can I build a model to simulate the shape? So the way to look at it is, yeah, we have 1,580 of these sort of grids. I know from the model I've been using, I can extract a lot of parameters from the model world, from the model atmosphere, and I can extract the parameter I find might be relevant. So that includes, for instance, the maximum velocity, the radius, the angle, the speed, the heading, things like this. The question then is, can I build a model on this and provide prediction for the shape? And well, the only thing you know really at the beginning is, okay, by construction, my maximum wind will be on that point, but I don't know anything about the rest. The one way you could go about it is try to simulate the actual magnitude on every single point. I'm not sure it's a good idea, but that's probably something that could be done. But the way I've attacked the problem is I turn to principal component analysis to reduce the number of dimensions, but also to focus only on the key modes of viability in my wind field. And this is what I'll be showing here. So if you're not familiar with this PCA analysis, one way to look at it is you're taking your data and you're projecting it on a different vector basis. What it really allows you to do is take any given target, any given wind field you have, and reconstruct it from the mean, which is, so that this is the mean wind field. If you take all of the 1,580 and you compute the average value of the wind field, you'll get to that point. And what PCA does is then say, I can reconstruct a target starting from there, and with the principal components, which are those fields or vectors, I can characterize the departure from the mean. And you do that with weights or coordinates, which are these WIs that I've put here. And in what I'll be showing, I'm only considering the first three principal components, and that is roughly explaining 2/3 of the viability in the data. So what we're doing is saying, I can take any given target, and I'll start from the mean, and then I'll add the value W1 times that component, value W2 times the second one, and value W3 times the third one. Another way to look at that is really that you're formulating a model in that way. It is a model of 3 parameters. If you give me the value of W1, W2, and W3, I can reconstruct a wind field. So I'll take the mean, add the W1 to the first PCA, W2 to the second, W3 to the third, then multiply by the VM because everything was normalized, and I'll get to a wind field that is really, it will be very close to the actual wind field, provided I've got the good values of W1, W2, and W3. And that's my model. So the key step here is, can we predict that? If we can somehow attack this idea, from having knowledge of a bunch of parameters, can I predict W1, for instance? So that's what I'll be showing now. So the predictors we're using in this model, well, I'm using everything that would be available in the CAT model, because that's the framework I work in. That means all the track and wind parameters I discussed, and also the 6 hourly change. So it's good to know about the size of the storm. It's also good to know if it's actually shrinking or increasing, and things like this. So these will be a total of 18 parameters. And at that stage, well, that's where I started using all the algorithm that Eugene taught me and trying to build models for my weights. And then I looked at the corresponding wind field. And the corresponding wind field were very close to the mean wind field. So Eugene told me that it actually makes sense because all the machine learning tools I was using were trying to model the mean. That's what they're built for. And it started to point me towards the direction of quantile regression instead. So what quantile regression does is, instead of actually trying to model the mean, you're trying to model a specified quantile in the distribution of your response. For W1, I will be targeting whichever quantile I decide. So you can build a model to predict the 95th quantile in the distribution of W1, given a certain set of input values. And that's great. So there's quite a few of those you can use, but usually you need to build a different model for every quantile in your distribution. And then we run into quantile regression forests, as turned out to be a bit of a magic algorithm for me. So that's what I've been using, because you can actually build one model that will let you predict any quantile in the distribution. So to give a bit of an example here, just a sensitivity test, I can use all my 30 storm and 1500 targets, build a model for W1, and then I can try and predict. What I've done here is to set every one of my 18 inputs as their mean value, and that's the black line. So the black CDF here, and you can see that for W1, if you look at the probability of having a W1 negative, it will be around 50%. And then you can start changing the value. So instead of having everything to the mean, I changed the radius to 20 kilometers or 240 kilometers, just sort of two extremes. And you see how the model distribution, the response, varies. Quite interestingly, it's not just a translation of the distribution. There's a bit more happening, which in the context of CAT modeling is something I really like. Introduce a lot more randomness in there by having distribution randomized. Then to do these things a little bit more properly, we did an actual leave one out evaluation of this method, but not, so we have 1580 targets, but they're very, very self-correlated. So the leave one out was done on the storm level then. So every time I take 29 storms, leave one out for evaluation. On the 29th storm, I'll do my principal component decomposition. I will build my quantum regression forest. And then I will predict the weights, the W1 in that case, for the storm I left out. And you can predict any quantile you want. And in that case, I've been predicting the median, which is the black line, as well as the 05, 25th, 75th, and 95th quantiles. The reason for this is that this allows to draw confidence intervals. So it's between the 5th and the 95th, you get your 90% confidence interval for the predictions. And same for the 50%, which is shown here as well. So this is for the first storm I left out. The red line will be the observed value, so the one from the actual left out storm. And then you wouldn't expect the median to be matching the red line. But actually, it's good to see that when you have swings in the red line, the confidence interval swings as well. It's also good to see that it's just one storm. It is pretty much only 10% of the points, the red points, that are outside of the confidence interval. So it seems that it's sort of bracketing the range of values in the right space. You probably see where I'm going next, which leave one out, we can repeat it 30 times, so we can have a picture of the whole thing. And there's no point to look at the details of that plot. But here again, the idea is sort of repeated the leave one out 30 times. So every storm has been evaluated as a left out storm. And these are all the samples, they're ordered in increasing median prediction. But again, you have 90% confidence interval. And the thing that really is to take out of there is, if we look at the CI90 that I put on the top, there are This is 92% of the observed value that fall in the 90% prediction interval, and 55 that fall in the 50% interval. So it seems pretty satisfying in that sense. I've repeated that for the other two weights, the W2, W3, and again, we have this feeling that the model is able to really sort of capture the variability we're after in that exercise. So how do we apply that within a CAT model? And that's where you would, as I did before, you would start and first randomly sample a quantile for your first weight. So that's W1. And then use your model, which you can predict your weight W1 conditional on the inputs you have, so the velocity, radius, angle, and so on. But then once you have W1, you can actually throw it in a bunch of predictors because you know it, and you might as well have some dependency between your weights. So you can randomly sample for W2 value, and you can model that W2 value is now conditional on your input, but also conditional on W1. And you can then do the same for W3, and then you can repeat that at the next time. And at the next time, you can actually predict conditional on the previous time step. So you can build some memory in your wind field through that way. And well, yeah, you can keep going until the end like this. I don't actually know how I'm going to stop yet. I'll probably just wrap it in. Okay, now one example beyond CAT modeling where I think this can be useful is to provide some quick way of having a probabilistic forecast model. So this is from this morning. So this is, when I left this morning, it was actually what I took on my computer screen. And that is a storm that has probably hit Taiwan now. So this is the sort of information you get from the Japan Meteorological Agency. And they will give you a forecast. Well, first this is the state of the storm right now, and that will give you a forecast at every 3 hours. And these are essentially the parameters I've been discussing. So when a storm is at 6 hours before landfall, they will tell you the information that needs to go into my model, such as the position of the storm, where it's heading, the pressure, and so on. So I can run this model that we've built, and take the example here of what would have happened if we had tried to build a model for those two snapshots on the left. So you can randomly sample in the way I've been discussing, and you'll get some wind fields. So that's the top here is one example of a randomly sampled wind field that characterizes that one. And on the bottom here, you'll get an example of the characterize the bottom one. So first, we see that we have now a wind field that are able to cope with the shape. So this shape we couldn't catch before, we can now catch it. But what this really allows you to do is keep on sampling. So you can go and do that 1,000 or 10,000 times. And every time, look at, for instance, do I reach the category 1 threshold on every box in here? And you can then just by dividing by the number of simulation get an idea of the probability of reaching the Cat 1. So you can, by coming back to a case like this, instead of having these sort of warnings, you can have a much better idea of where you think you might have a Cat 1 as a forecast. And now I'll finish. So first, in terms of the wind field, well, I think modeling the weights and using quantile regression forest is really helping both to capture the shapes we couldn't capture before, but also I think it's throwing a lot more variability in the model, which in the context of CAT modeling is exactly what we want. That might help better represent the risk and capture things like Sandy was, but there's clearly a problem with data because I could sit and model another 30 and so on, but that's not going to be enough. So I think that for us to go forward in that sense, we really need to start sharing these things. So that's just food for thought, I suppose. In terms of machine learning, well, I think there's plenty of scope of places for model upgrade. But I think out of the challenges I listed, there's still this one that will be a problem in many places in the model is the way we are actually simulating things is we want to extrapolate way beyond the training set. So we need to find a way to model differently, let's say. And I've put that as the end without necessarily understanding all of it, but Eugene's been saying that should be my homework for next year, so I think Bayesian approach will be the way to go. Thank you very much.
Don't have a great deal of time, but I'm sure you all have questions for Thomas, so let's make them quick. What are the questions?
Thanks, Thomas. Just quick. Just quickly, do you experience problems with quantile crossing using the quantile rainforest?
And the answer is no, because with quantile regression forest, you only build one model. Like, you're probably thinking of linear quantile regression where there's a model for every quantile, so not with quantile. That's one of the reasons it's magic.
I would have given the same answer. Yes, sir.
In terms of the models, you're using a combination of physics and sample data, aren't you? That. When you're looking at the sample data in the past, correct me if I'm wrong, but as time goes by, the geology of the Earth and the structures of the Earth and the temperatures change.
Yes.
And especially in recent years with like man-made global warming, etc., and the different periods,
Yeah.
does that mean you have to combine the physics knowledge of each time period to get accurate models of what damage is going to be done to understand that? Or is this something where in the future, if you can generate enough data and get a good enough physics model, you can maybe generate your own data more accurately than your sample data would be in the past?
Yeah, no, that's a really good point. And the answer is it depends what sort of risk you're trying to assess. And our clients are insurance, usually the insurance and reinsurance industry, and the typical contract will be 5 years. So you're looking at the risk now or in the next 5 years. So in that sense, you would try to include maybe an increase in the rate of hurricanes if you think that has happened, but that's reflecting what's happening now. We don't do a projection, we don't do climate projection in that sense because we're not trying to look at the risk in 50 years. If people wanted to insure for houses in 50 years, then yes, we would have to sort of come up with a way to include climate change or other things. Yeah, I think that's sort of the answer to the question. A little bit more.
One more question, please. Unfortunately, we have to get going soon.
Just on your first step with the PCA decomposition, why PCA and why not some other decomposition, say, only allows positive components? Because it's pretty difficult to have a negative wind. It's a vector, so you don't have a negative wind. So have you looked at doing something else besides PCA, or is it just the first step?
I haven't, and Eugene has been saying the same when I mentioned PCA. It's like he wasn't a big fan, but in my field, this is really, it's true we sort of throw that at every problem, but I think in that case it has if you look at the actual patterns of the first 3 PCA, you can really sort of get the physics behind what happened, and that's sort of why I like this method. I'm not familiar with other methods, to be honest, so I'll be happy to hear what.
Neural autoencoders, maybe.